Example 2. Using the definition of continuity at a point, find the points of continuity and discontinuity of the greatest integer function f of x equals int of x. So we have the graph here, which represents the integer function. But before we look at this and actually analyze it, I want to show you the graph in motion. So here's the integer function, and I'm going to just let this play. And what you notice is that every time that the green dot approaches the open circle, it jumps to the next integer value. So this is what we call a continuous graph everywhere except where it's discontinuous. What we can do is we can represent this graph as continuous except where it's not. And so let's take a look about how to do that. So as we look at this graph, we notice that it's discontinuous wherever there's a jump. These are the points of discontinuities. And you notice that these discontinuities happen at each integer value. So what we're going to say is that f is continuous everywhere except where x equals k, where k is an integer. So again, this means k is an integer. And that's how you're going to tell me where the integer function is continuous and discontinuous all at once. So if we look at this graph, which looks like to be y equals x plus 1, we can see that this thing looks to be continuous. So y equals f of x is continuous at x equals 0 because, well, if we think about the definition of being continuous, we know the limit as x approaches the x value we want, so x equals 0, of f of x is equal to f of that x value, so f of 0. Well, the limit as x approaches 0 of f of x, as we approach it, we get that the limit as x approaches 0 is 1, and f of 0, that's f of 0, is also 1. So we put the limit as x approaches 0 is equal to 1, and this is very important, f of 0 is equal to 1. You need both of those things to be continuous. The next thing we're going to do is talk about different types of discontinuities. So looking at these two graphs, they look very similar, and they actually have the same kind of discontinuity. Before I tell you what that kind of discontinuity is, we're going to determine the limit and the values. So for the graph of A, the limit as x approaches 0 of f of x is, and so if we look at the limit from the right and the limit from the left, we get that it's 1, and f of 0 is a whole. So if there's no value there, then we say f of 0 is undefined. Looking at part B, however, the limit as you approach 0 is also 1. However, f of 0 is this point right here, which is 2. But notice that these are not the same. And this is a very big deal because if the limit is not the same as the evaluated point, then that means that the function is not continuous. That's the definition. And we call both of these removable discontinuities. And we call them this because if you notice, it looks like we took a point and just took it out of the graph. So if this point was solid, this would be continuous. However, it's like we punched a hole in the graph, so it creates a removable discontinuity. Moving on to our next type of discontinuity, let's look at this graph. So the limit as x approaches 0 from the left is going to be 1, and the limit as we approach from the right is going to be 2. So therefore, the limit as x approaches 0 of f of x does not exist. And again, this is because the limit from the right is not equal to the limit from the left. We call this discontinuity a jump discontinuity. That's because to get from one point on the graph to the next, you have to jump or lift your pen and move to a completely different y value. We have two more types of discontinuities to look at. Looking at this type of discontinuity, this is the graph of y equals 1 over x squared. And as we approach the limit from the left, you can see we go off to infinity. And as we approach the limit from the right, we also go to infinity. So notice, limit from the left is infinity, limit from the right is infinity. However, the limit itself, so the limit as x approaches 0 of f of x, does not exist. This is because a limit, when you approach a number, has to be a number. Limit from lefts and rights are behavior. We call this an infinite discontinuity. Looking at our last one, we look at the graph of y equals sine of 1 over x. Now notice these x values right here. These are very small x values. So the limit, as we approach 0, that's complete chaos in there. That does not exist. It'll squiggle like that forever, and the more you zoom in, the more squiggles you're going to see. We call this an oscillating discontinuity. We call it this because it's just going to go up and down forever, and the more you zoom in, the faster it goes up and down.